In this video, we are going to look at partial derivatives. So we know from Calculus 1, if we're looking at a derivative dy dx, that indicates that the dependent variable is y and the independent variable is x. Now in two variables, z is the independent and x and y are both the independent variables. We're still going to use this notation in multivariable calculus, but the d gets replaced with this cursive d, like a delta almost. And now we have two different derivatives we can take, since there are two different independent variables. Depending on which one we choose, we may end up with different partial derivatives. Frequently, that's what happens. So here's the definition. A function of two variables and the partial derivative of f with respect to x, df dx, or f sub x, is defined this way. Notice that the x plus h is attached to the x part, minus f of xy over h. Or if I'm doing it with respect to y, df dy, where I've got now k goes to 0, and I have y plus k minus f of xy over k. So this is by definition. Let's go ahead and do an example in which we're asked to do this by the definition. So that's dz dx x is going to be equal to the limit, by definition, of h goes to 0 of the z. This is our function z. Instead of f, we're using the function z, so we'd be using z here instead of x, or f, excuse me, of x plus h and y minus our function z, xy, all over h, and this will be equal to the limit as h goes to 0. Now wherever I see x, I replace with x plus h. So I have x plus h squared minus 3x plus h multiplied by y plus y squared. Now all of this represents this piece. And then minus my original function. My original function is x squared minus 3xy plus y squared. And that is that portion. Divided by h. Now, if you have a tendency to get lost in your algebra, then I would recommend that you do this piece separately than this piece and go ahead and do the x plus h, and then down here the dx, or the y plus k down here separately. Simplify it and then subtract that off, then put it over h and then do the limit. So if you have a tendency to lose stuff algebraically, then I would recommend that you do that as h approaches 0. So I'm going to go ahead and expand this out. So I have x squared plus 2xh plus h squared minus 3x minus 3h multiplied by y's, don't forget those y's, plus y squared, minus x squared plus 3xy plus y squared, excuse me, minus, be a minus, see, I'm doing it too, all over h. My x squareds cancel themselves out. I have, let me see what else cancels out. That's about it. Do I have a 3xy? Yep, these cancel out. Now, what I'm left with then is the limit as h goes to 0. Oh, also, this cancels themselves out. And then what I'm left with is limit as h goes to 0 of 2xh plus h squared, not much else, minus 3hy all over h. Now that's an h, that's a terrible h. Here's a check. At this point, I should have every single term with an h attached to it as part of the factor. If I don't, I must have made a mistake somewhere, because the next step is I'm going to go ahead and factor out an h, add to the numerator, leaving me 2x plus h minus 3y, and divided by h. So I end up with, as h goes to 0, just 2x minus 3y. Now we're going to do the same exact function, but now we're going to do it with respect to y. So it is going to be dz dy is equal to the limit as k approaches 0 of my function z of x, and then it's y plus k minus my function z, y, and x and y over k. Similar to what I did up above. It's going to be the limit as k goes to 0 of, now everywhere I see y, I replace with y plus k, so this is going to be x squared minus 3x, and then y plus k, plus, and this is y plus k, the quantity squared. Again, this represents just this. I guess I should do that in blue. So this represents just this portion. And then I have minus, and then my original function, so x squared minus 3xy plus y squared. That's this. All over k. And so the limit as k approaches 0 of x squared minus 3xy and minus 3xk plus y squared plus 2yk plus k squared minus x squared plus 3xy minus y squared all over k. And again, we're going to start canceling out like terms. And a check to yourself, when you get down to this point, the limit as k goes to 0. In the numerator, if each and every one of my remaining terms does not have a k attached to it, then I must have done something wrong, and that's k. I want to keep writing h, but it's k. I'm going to factor out of the numerator a k, leaving me 3x plus 2y plus k divided by k. My k's are going to cancel, leaving me, and as a direct substitution as well, I'm going to have negative 3x plus 2y. Now you notice that these are not the same thing. That when I went with respect to x, I got this, and with respect to y, I've got this. If we're doing it in 3 variables, then of course I have h, k, and we use m for when we get into 3 variables. Now I am not going to make you do the definition of the derivative for 3 variables. What I am going to do, however, is look at, let me lock the rotation again, is look at derivatives. And what we know is that everything we learned in Calculus 1 and Chapter 3 in this OpenStax book still apply. The thing that really is the difference is that whatever one that we are not taking the derivative of with respect to is like a constant. We're going to treat it as a constant. So if I'm asked to find dz dx, then my y is going to be treated like a constant. So let's go ahead and do this first one. I have dz, the partial derivative of z with respect to x, which in this case, let me do it with the notation so you can see what's going on here, is going to be the x to the 8th e to the 3y. Now, this is going to be considered a constant because y is not going to be a part of the derivative because it's with respect to x. And so I end up with my 8x raised to the 7th e to the 3y because that's just a constant. So I'm using the constant rule. Remember when I did d dx of some constant multiplied by x raised to the n, this ends up becoming my constant times n x raised to the n minus 1. Now, it's not a full derivative, it's a partial derivative. I'm doing the derivative of z with respect to x alone, and so that's what I get when I have the respect to x. Now, I'm going to do the derivative now with respect to y. So this is going to be x to the 8th e to the 3y. This is going to be considered a constant. So this is going to be equal x to the 8th, e to the 3y multiplied by 3. So this is equal to 3x to the 8th, e to the 3y. And the derivative I would be doing is, so dx in general. Well, let's do u, du. Let's do it with du. Of some constant e to some function u is going to be the constant e to the some function u and u prime. Okay. Now, what happens when we are looking at the natural log? We're going to use the natural log function, and I'm going to do it for each one. And so I'm going to have the dz dx is going to be equal to 1 over the x to the 6th plus y to the 4th multiplied by 6x raised to the 5th. So what I'm using is du of the natural log of u is 1 over u prime. Because this will be considered a constant with respect to x, that's why it's just 6x to the 5th. Now let's go ahead and do dz dy. It's also going to be 1 over x to the 6th plus y to the 4th, but now it's going to be 4y to the 3rd. All right, let's take a look at my next example. For my next example, and notice that we have the derivative of my function with respect to y. This is the notation for multivariable. So I'm going to do the derivative of my function with respect to y. So anything that has an x, I'm going to treat as a constant. So I'm going to be doing the product rule. I'm going to do this as the product rule, where I have u is going to be e to the xy, so u prime, by the product rule. And now remember, my y is my independent and x is like a constant. I'm going to treat it like a constant. So this is going to be e to the xy multiplied by x, because the x is like a 5. So it'd be 5y. So it's just 5. It's just the x. And then my v is going to be the cosine of x and then the sine of y. Now remember, x is the constant. It's going to be treated as a constant. So v prime is going to be the cosine of x multiplied by, well, the whole derivative is the derivative of y. So this is going to be multiplied by the cosine of y. Now I'm going to use my derivative with respect to just y is going to be equal to, so this replaces the y prime thing that we had before. This notation replaces the y prime when we were only in one variable. It's going to be equal to my e to the xy x multiplied by the cosine x, the sine of y. So this is u prime v plus, I'm going to write my u first, so it's e to the xy, so this is u. Now I'm going to multiply by my u prime, which is the cosine of x, the cosine of y, and that's my v prime. And that's my final answer. That's it. So my answer is right here. It's kind of cool. I don't know. I think it's kind of cool. Now, we have 3 variables. Not much is changing. I have this, which is a function, and then I have this, which is a function. So once again, I'm going to do my u. My u is going to be just z. My u prime is going to be just 1. My v is going to be the sine of my angle. And so v prime is going to be the cosine of the xy squared plus 2z multiplied by the derivative of my angle, which is just going to be 2. Because what I'm using here is I'm doing d theta of the sine of theta is equal to the cosine of theta multiplied by theta prime. Where if I take a look at this, the only thing that is not a constant is the 2 times z. That xy is going to be treated as a constant. So dw dz is going to be equal to 1 multiplied by the sine of xy squared plus 2z plus, because this is my u prime v, plus z multiplied by 2, so I'm going to shove a 2 right there, the cosine of xy squared plus 2z. So that is going to be my v prime u. I love these, but they're also, you can get lost. So I'd recommend when we first started learning derivatives, we first started learning the product rule and the quotient rule and the chain rule, is really consider actually labeling everything until you get really good at this. And then you don't necessarily, or if you're like, man, I'm just going to jump in, and that's okay too. It's okay too. Go ahead and just jump right in. Both feet, jump right in. Okay, so let me move that out of the way. What does this mean when we're doing the partial derivatives? Well, if we remove the limit portion of the definition, then we just have the difference quotient. Looking at with respect to x, we just have the difference quotient, which is the equation of the slope of the secant through x1y and the output. Remember, in 3 space, so it is x, y are the 2 inputs, z or f of my ordered pairs is the output. And the second ordered pair, which is x sub 2y, f of x sub 2y, where h is the difference between x1 and x2. So we have this. That's a secant line. That's all it is. It's a secant line. Now, the secant line happens to be running parallel to the x-axis, which, because I'm doing it with respect to x, which means the slope of the secant line represents the average rate of change of the function as we travel parallel. I think there might be missing parallel. There might be an L missing there. Now it's there. To the x-axis. As h goes to 0, the slope of the secant line approaches the slope of the tangent line through that point we're looking at. Similarly, if we choose y instead of x, then the secant line is going to be parallel to the y-axis. So, the partial derivative with respect to x represents the slope of the tangent line passing through this point parallel to the x-axis. Which, if we do it with respect to y, then it's parallel to the y-axis. If we do it with respect to z, it's parallel to the z-axis. The slope of the tangent line can go in any direction, however, when I'm not parallel to the x-axis, so any axis, as long as I'm going through the same point, is called directional derivatives, and we will look at that next quarter in section 4.6. If I am trying to determine what the sign of the partial derivative is at some given point, then what I do is I go to that point, so I'm going to go to the point 1, 1, so here's 1 and here is 1. So I am back here somewhere, like right about there. Let me put a dot right about there. And I can see on the surface, if I were to do a tangent line, it looks like the slope is increasing. So this looks like it's positive by just looking at the shape. At negative 1, 1, so here's negative 1 and here's 1, so it looks like we're about right there. And it looks like that if I were to draw the tangent, that would be a negative. If I look at positive 1, so it's about right here. And it looks like I'm going uphill, so that's positive as well. At 0, 0, it looks like we're kind of at the bottom, so it looks like it's going to be 0. So it looks like it's right at the bottom. We can also determine the sign of the partial derivative if we look at the contour map. Now, in this example, it looks like it's probably an elliptic paraboloid of the form z is equal to x squared plus y squared. It just kind of looks like it is. Now, if we do the contour map on the xy plane, we can estimate what my partial derivative with respect to x is at 1, 1, looking at C1 and C2. Now, C2 is the circle centered at the origin, passing through 0, 0, and the C2 is the wider one. So here's this. Looks like this is the shape. So it looks like a elliptical paraboloid. And here's C1, and here's C2. So as I go from my first ordered pair to my ordered triplet to my second ordered triplet in this direction, that it looks like that my f of 2 should be larger than my f of 1. So f of 2 minus f of 1 divided by h should be greater than 0. So looking at my contour map, we can see that f of 1 and then h plus 1 is increasing when h is 0. So if h is greater than 0, then clearly f sub 2 is larger than f sub 1 and vice versa. So that leads us to finding partial derivatives at the given values. So I'm going to do the partial derivative with respect to x. So the partial derivative with respect to x is equal to, now remember, this, because it is a function of y, is going to be considered a constant. So what I'm really just doing the derivative of is e to the negative x multiplied by my constant, which is the cosine of y, multiplied by the derivative of negative x, which is just negative 1. So now I'm going to evaluate dz, well, it's not dz, partial derivative. The partial derivative of z with respect to x, evaluated at the ordered pair 0, 1, is going to be equal to e to the 0, the cosine of 1, and then multiplied by a negative 1, which gives me just negative cosine of 1, and we're probably going to be in radians. I'm going to leave it like that. I'm just going to leave it like that. Let's look at our next example. We want us to do the partial derivative of respect to x, that's this one, evaluated at this point. So we're going to have to find the partial derivatives. F of, let me see the partial derivative. So df with respect to x is going to be equal to, well, this is like saying I have x times 3 over x minus 3. So I'm going to use the quotient rule probably. I think I'm going to use the chain rule. So I'm going to write this as xy multiplied by x minus y raised to the negative 1. I just don't like to do the quotient rule. Don't ask me. Whatever. So I'm going to do the derivative of x, which is just going to give me y multiplied by x minus y raised to the negative 1. And then plus, I'm using the product rule here. And then I'm going to have xy multiplied by x minus y raised to the negative 2 multiplied by the negative 1, because the power came down out front, and multiplied by 1, because that's a derivative of xy. So kind of ugly, but not bad. Let's go ahead and put our numbers in. So the partial derivative of f with respect to x evaluated at 2, negative 2 is going to be equal to negative 2, and then this will go in the denominator, and then it's going to be 2 minus a negative 2 plus, and let me see, this is going to be negative 2 and negative 2, and then in the denominator I'm going to have 2 minus a negative 2, the quantity squared, which is going to give me negative 2 over 4, and this will become plus, and then it'll be 4 over, what is that, 4 squared? Yeah, 4 squared, which is 16. So my final answer is negative 4 over 16, or in other words, negative 1/4. Okay, so now let's do the derivative, partial derivative, with respect to y. Okay, I'm going to treat it the same way, and so I'm going to have my derivative of my first would be just x, and then multiplied by x minus y raised to the negative 1, and then I'm going to bring that negative 1 down out front, and I have the xy there, so don't forget the xy, and then x minus y raised to the negative 2, and multiplied by the derivative of x minus y, which is a negative 1 this time. So I'm going to do my partial derivative, not d, it's a partial derivative with respect to y, evaluated at 2, negative 2. So this is 2 in the numerator, and it's still 2 minus a negative 2 in the denominator in that first term. And this is going to be a plus this time, and then 2 multiplied by a negative 2, and then in the denominator I'm going to have 2 minus a negative 2, the quantity squared. So I end up with 2 over 4, and then minus 2 So that's 4 over 16 still. In this case, gives me 4 over 16, which is positive 1/4. So that tells me as my derivative with respect to, let's bring this into graphing, if you want to think of it that way. My partial derivative with respect to x, which is this one, tells me as I'm running parallel to the x-axis at this point, my shape is decreasing in the x direction, and my y is increasing because I'm running, this is running parallel to the y-axis. This derivative is running parallel to the y-axis, and it's increasing. So as my x is decreasing, my y is increasing. So it's going to help us when we start thinking about the graphs. Now we're going to keep going, and we're going to say, well, what happens if we want to do partial derivatives? And we're going to say, well, we get to do those too. In 2 space, let me move this over a little bit. There we go. In 2 space, there are 4 second-order partial derivatives. There's the partial derivative of f with respect to x twice. There's a partial derivative of f with respect to first y and then x, the partial derivative of x then to y, or that's the partial derivative with y with respect to itself twice. So order matters. So if you see the partial f with y then x, that means we do the derivative with respect to y first and then x. If you see x and then y, that means you do the partial derivative with x first and then respect to y. And when we see these with different variables, these are called mixed partial derivatives. Now, of course, in 3 space, then we get even more exciting things to do in 3 space. So this y is first, so I'm going to do the derivative with respect to y first. So f of y. This is going to be 1 over x minus 1 and then times -1, which is -1 over x minus y. Now I'm going to do the derivative, so f of y with respect to x. I'm going to rewrite this as -1 x minus y raised to the -1. So the derivative of this, the second order mixed partial derivative, is going to be the -1 multiplied by the power of -1, x minus y raised to the -2, and the derivative of x, which is 1. So I end up with 1 over x minus y raised to the 2. On my next example, I'm going to do the mixed partial derivatives, where I'm going to do it with respect to y, then x, and then respect to x, then y. So first I'm going to do the derivative of z with respect to y first. That means e to the x is just a constant, so it's e to the x. And the derivative of the tangent is secant squared of y times the derivative of y, which is 1. Now, the derivative of z dx, partial derivative of x, partial derivative of y is going to be this derivative with respect to x. So the secant squared of y is just a constant now. So I'm going to do the derivative of e to the x, which is e to the x all day long. This is e to the x, and then secant squared of y just comes along because it's a constant. Now we're going to do it the other way. So the partial derivative of z with respect to x first. So if we do the partial derivative of z with respect to x, that means this is my function and this is a constant just coming along for the ride. And so this is going to be e to the x, the tangent of y. Now I'm going to do my second partial derivative with respect to y. So dy dx, not zx. So now this is a constant and this is the function, so it's e to the x. Actually, let me do this in green. This is going to be e to the x, and then the derivative of tangent is secant squared of y. There are times when this happens, when my derivative with respect to x then y equals the same derivative with y with respect to x. And we call that, that when that happens, we have Clairaut's theorem. So we'll talk about that in a minute. Now, this one is I want to do the derivative. Now, notice I have a z in here. So I want to find the partial second order derivative with y first, then x, and then evaluate it for the derivative at z. So I'm going to do d2f. I'm going to do it all together this time. dx, partial derivative with respect to y, which is going to be equal to the partial derivative with respect to x of a partial derivative with respect to y of x to the third y z squared. So now you can start seeing what happens when it comes together. For this, we know that we're doing it with respect to y, so the partial derivative with respect to x, I'm going to pull out everything that's a constant, which is going to be x to the third z squared. And I'm doing the partial derivative of y of just y. This gives me the partial derivative with respect to x of, I have x cubed z squared, and then the derivative of y with respect to y is just 1. Now I'm going to do the partial derivative with respect to x. So that means z squared is a constant. I can bring that out. And that should be x cubed. Put that back as x cubed. And so I do the derivative of x with respect to x. So I get 3z squared x squared. And that's my final answer. Now I want you to do your partial derivatives however it makes it easy for you. Whether it makes it easy for you to do it in this one string like I did here, like this, or if you do it by doing partials one at a time like I did up above, whichever way is the easiest for you to be able to keep track of your partial derivatives. They're also asking me to do the derivative of z, do the partial derivative with respect to z, and then evaluate it at 1, 1, 1. So dz of x cubed y z squared. X cubed is a constant, y is a constant, so the partial derivative with respect to z of z cubed is going to be 2x cubed y z, I don't know why I keep changing the powers. That's just 2, and this is power of 1. Now, the partial derivative with respect to z, evaluated at 1, 1, 1, is going to be equal to 2 multiplied by 1, multiplied by 1, multiplied by 1, which is a positive 2. So that tells me, if I were to graph this at that very moment, that z is increasing at this point because this is a positive value. So z is increasing at this point as we're running parallel to the z-axis. My z values are increasing at that moment. Now we talked a little bit about this just a few moments ago. That under certain conditions, like we had at one of our examples, the partial derivative with respect to x then y, and the partial derivative of y then in respect to x. Sometimes these are true under certain conditions, which brings us to this theorem. And this guarantees as long as the mixed second-order derivatives are continuous, the order in which we choose them does not matter, and this can be extended to higher-order derivatives as well. So that's it for this section.